Right. So, okay. So Fauzi has a bachelor degree in math. Fauzi, correct me if I'm wrong. So he's a bachelor degree from Cairo University in Egypt. And then he went for a postgraduate diploma in the International Center for Theoretical Physics in Trieste, Italy. And this is where I did my diploma. So he came 1 year after me. And then after the diploma, he started PhD in the Berlin Mathematics Research Center, which is called Math Plus and something like this. And he's a very close friend of me in PMS because his office is right below my office. And whenever I feel to understand something in algebraic geometry in my research work, I just go to his office and he explains me very well. And so in that sense, I would consider him as my teacher as well. And now he would become your teacher. So Fauzi is a very great explainer of very deep ideas. I mean, algebraic geometry is really rigid subject. And we were looking for somebody who can, explain it to audience with mixed background. And I mean, out of the whole Berlin and maybe Trieste, we could only find Fauzi to do that job. And the good thing is that he agreed because he has a very busy schedule already. And yeah, so thank you, Fauzi, and you can continue now.
Thank you very much, my dear friend. I hope you didn't raise the expectations of people so much here. I'm really grateful for your nice words. Thank you also for the invitation. It is a pleasure to be here. Also, since this is first time I'm giving such a lecture to a large audience, I'm not sure how things will be smooth, to how smooth it will be, but please, if you have any feedback afterwards, any comments, please write me somehow, and I will take them into considerations in next lectures. So I want to actually start by saying some small comment before I start the actual lecture. Is algebraic geometry is relevant to also people in industry and also people in applied mathematics. Just yesterday, I was attending a talk about how to solve some kind of differential equations, which comes from like the dynamical systems and neuroscience and geoscience and stuff like this. And in the middle of nowhere, this guy just used the blow up, which comes from algebraic geometry, and it turns out it is useful because it enables them to study like vector fields on some manifolds, and this helps them solve differential equations. So even if you don't care about algebraic geometry per se, and if you don't want to do algebraic geometry, you hate algebraic geometry, you might be forced to do algebraic geometry, I'm sad to tell you. Anyhow, I think now I should start sharing my screen. Yes, so I just ask everyone, please, if they can mute themselves, because this might have an effect.
Hello. Hello, can you hear me? Hello, can you hear me?
Okay.
Hello.
Okay. So I think some one of the moderators, they can mute everyone, and like to be allowed to speak, you might like require a specific request. I'm not sure how it is done, but it should be doable. Shan, can you hear me?
But you can continue, sorry.
It's okay. Okay. So I shall start. Please, if you have any questions, you might also try to write them in the chat, or just raise your hand or participate. I might not be able to track the chat all the time, but Shah, please, if you find someone writing something, just tell me, okay? So let's start. So the aim of this talk is to start actually very slowly, and just to tell you what is algebraic geometry and why you should care about it, even if you don't like it. And we will not cover any advanced material, just it is the motivations and the background which is relevant to us today. Okay, so algebraic geometry aims to understand solutions of polynomial equations. And those solutions or those roots of polynomial equations, we call them algebraic sets. That's the basic idea. So the key word here is now understand. What does it mean to understand something? Well, in our context, understanding means several things to several people, depending on who you talk to. Well, it can mean you want to compute things explicitly. So, for example, you want to have an algorithm or a computer program that solves the equation for you. For example, in linear algebra, we want to solve linear equations, and we have methods to do this. For example, Gauss elimination method. We can use matrices and stuff like that. And you can code a computer program that's given a linear equation or a linear or a system of linear equations. It tells you whether a solution exists or not, and if it exists, it produces one, and also it can, for example, parameterize those solutions. So that's one way you can understand solutions of polynomial equations, and that's also part of algebraic geometry. Another thing you can do is to do it numerically. You don't want to have an exact solutions, but you also want to have an approximations. That's the numerical algebraic geometry. Another thing that you can do, which we do with linear equations, is to parameterize the solutions. What do I mean by parameterizing the solutions? It means you have some parameter, t, for example, and you write your solutions x, y, z, let's say, in terms of t. So you can say x equal 2t plus 1, y is t squared, and z equals 3t over t plus 1. And that's some formulas of x, y, z, which are your unknowns, your variables in terms of another parameter, and this parameter is allowed to be anything. And every time you put t, you get a solution. That's what I mean by parameterizing. And of course, later on, we will see example of this. And actually, we will discuss parameterizing solutions a lot because it's relevant for people who want to do calculus and who want to calculate integrals. Another thing, which is what algebraic geometry is all about for most people, is to study the geometry of these solutions. So, I mean, algebraic geometry is after all some kind of geometry, so you want to study the geometry of solutions. But here there is an implicit assumption, which is that those solutions of polynomial equations form some kind of a geometric shape. And that's true. And before we go on, I want to also give you a slogan that you should remember, and hopefully by the end of the fourth lecture, you will have a better understanding of what this slogan means. So this is a French quote from a mathematician, Sophie Germain. So she said, and pardon my French, l'algèbre n'est qu'une géométrie écrite, la géométrie n'est qu'une algèbre figurée, which means that algebra is nothing by a written geometry, and geometry is nothing by a visualized algebra. And you might think this is only true because it is algebraic geometry, but, and hopefully this will surprise you, next time I will also tell you how you can implement this vision in differential geometry. And that in, for example, for manifolds, many geometric things can be seen from just the point of view of algebra. Almost everything you care about, vector fields, differential forms, everything can be viewed from the point of view of algebra. So the key term here, algebra, doesn't mean high school algebra. It means like algebras, as in algebra. I mean, we will come to this later on. It might not be clear now. Anyhow, so let's start with the definition. So, and this is a preliminary version. So the definition will change later on, but here just to give you an idea and to work out some examples. So if we start by some non-constant polynomial with real coefficients, let's study its roots. So the set of all points on the real plane, which after substitution in this equation, we get 0, right? So just roots of one polynomial in two equations. Okay, so the most easiest example is a line. So here I think this equation is wrong. That's the first typo. So actually here, this is y minus 2x minus 1. So this is a line in R2, something we are all familiar with. Another example is a circle. So we can have this equation, x squared plus y squared minus 1. You study the solutions of this, which means you brought this equation equal to 0. So this is equivalent to x squared plus y squared equal to 1, which is a circle in real plane, right? Because here I'm just giving you the equation, and you want to make this equal to 0 and study the roots of this equation. Okay, now let's do some non-trivial stuff, some non-trivial examples that probably we didn't see in high school or first year mathematics in university. So this equation, here you have an equation in x and y is squared, x is at most cubic degree. So, and if you plot this, you get a curve like this, right? We call this a cubic curve because simply the highest power is 3. And it is special because this kind of curve is called an elliptic curve. And it is it has a lot of mathematical structures. So for example, you can define a group structure, and this group structure is important if you want to study number theory, for example, and it also has applications, real-world applications. For example, in cryptography, if you want to cipher something, you can use elliptic curves for this. I mean, the group structure of the elliptic curve. Okay, more elliptic curves. We just changed 1. So here you notice that the difference between the two equations is here we have -1, here we don't 1. But you see the structures, the shape of the geometry has a lot of differences. For example, here you have 2 components. Here you have just 1 component, and this component is bounded. This component is in some sense non-bounded. So even a small change in the equation have drastic geometric consequences. And one aim of algebraic geometry is to try to figure out those differences, not by looking into pictures, but by trying to analyze the equation itself and using algebra to understand this. Well, more examples. Cubic curve is still, so here y squared is still x cubed, but here we have just changed it. We have like quadratic term in x. And as you see here, we have a totally different geometric structure. For example, here you have, I don't know how to get a pen. Can you see my mouse? My pointer. Okay. So here you see this point. It is a weird point because in all examples before, you see at any point you can write or can draw a tangent line, and at every point there is a unique tangent line. Here somehow you have this point, and there are 2 obvious tangent lines. For example, you can draw a tangent line along this way or along this way. So that's a peculiar kind of behavior, and that's a different thing, and you just get it by just manipulating the equations. And something else is like that. Here you can also argue that you have more than 1 tangent line, and you see here we have this kind of node. Here you can say that the curve is not smooth, right? This curve is not smooth. I'm not sure I said it or not, but such a solution set is called a real algebraic curve. So here I said a real algebraic set, but the correct thing is in the title, a real algebraic curve. So a real algebraic curve is just a set of solutions of one polynomial equation in 2 variables for now. Okay, so after analyzing those examples, we might think there are some properties that we can start to emerge and that we can notice. For example, some curves are connected, meaning they have 1 component. For example, this one here has 1 component. You are not having 2 separate things. This one is also connected. You cannot separate the points from each other, but this one has 2 connected components. There are 2 things which are disjoint from each other, and this one here is still connected. So some of them are connected, for example, those given by these equations, and some are not connected and having several components. As a geometer, the first question to come to you should be the following questions. First is about enumeration. Can we enumerate the components, those components? So how many components can a real algebraic curve have? And can we calculate the number of components algebraically? meaning given the equation, can we calculate this number of components? And for example, you can ask, can the number of components be infinite or not? If it is finite, how many? Can we have some bound? Can we say it must be less than 15, or it must be greater than 2? For example, those cubic equations that we have discussed before, those ones, you notice it has either 2 components or 1 component. Can it has 3 components? As a geometer, that's interesting. And it turns out that for cubic equations, the answer is no. It can have at most 2, but that's not easy to see. And in general, there are bounds. So, and I think we will discuss this when we talk about algebraic curves in a later lecture. Okay, so that's an example of a question which is interesting to algebraic geometers. Some of those questions might be easy to answer. Some of them can be answered in 5 minutes. For example, this question here about these kind of points, you can answer it in 5 minutes. Some of them can take you a few hours to figure out. Some of them can take you a few months or even years to fully settle down. And that's, I think, the beauty of algebraic geometry. A priori, you don't know how easy the question is, and it can turn out to be very easy or very difficult or anywhere in between. And you have to really think about why this is the case. Okay. Other features of curves is this tangent issue. So some curves have the property that at every point they have a unique tangent, meaning only one tangent line. And some other curves have the opposite way, that there are at least some points at which there are several tangent lines. And also this poses some geometric questions. Well, how many points can we have which have multiple tangent lines? So can we have infinite number of points which have multiple tangent lines? Is this number of points only finite? And can we compute those points from the equation? That's a geometric question. Lines are geometric objects. Next is something very important, that even though we started doing real solutions, real numbers are not enough. Because, my friends, if we look, for example, for such an equation, we put this equal to 0, we want a real solutions. There is none, simply because you don't have square roots of -1. Even in one variable, you don't have a solution of equation x squared plus 1 equals 0. So if we are interested in solutions of equations, we have to go to complex numbers. Well, of course, you can say, this equation have no solutions. I want to study the geometry of empty sets. Okay, you might. I mean, the empty set is empty. You don't study. There is no geometry to study. So if you want to have something to study, you want to have a space. So, and this is also a feature. You look here. Everything here, you have some geometric shape. You have a circle. You have a line. You have a curve, whatever this means. You have some stuff to study. You have to ask questions. So you want a non-empty set, and that necessitates that you want to go to complex numbers. Okay. Later on, we will see that even doing geometry in complex numbers alone, so in C squared, is not enough, and we have to go to something called the projective space. But that's not the story that we are going to talk about today. That will be covered maybe, I think, next time. So let's do some more examples. Now, instead of having one equation, one algebraic curve, let's do 2 algebraic curves together. We have 2 lines, they intersect in 1 point. Those are my 2 equations. Remember, I just give you the equation and you have to say this equal to 0. Those are 2 lines, they intersect in 1 point. High school stuff. Okay, let's go 1 dimension higher. We have a parabola, we have a line, they intersect in 2 points. Okay, so you might ask, why are you still doing real numbers even though you said we should do complex numbers? Well, that's because I can't visualize complex numbers. So for the purpose of this talk, I will just stick to real numbers. But when we start the real mathematical treatment, giving you a formal definition, stating a theorem, we will have to use complex numbers most of the time. But just now to give you a flavor, some examples, to also notice some features, we will stick to real numbers. And also, in fact, many features that we want to expose appear already in real numbers if you choose the correct examples, which I think I did here. So it will give you the required intuition and features that you should see. Okay, so here we have a parabola, we have a line, the intersecting 2 points. That's really nice. Let's go one dimension higher. So here we have a parabola, and we have an ellipse, and we see the intersect in 4 points, right? So you might start to notice some facts that here, this is of degree 2, this is of degree 1, they meet in 2 points. This is of degree 2, this is of degree 2, they meet in 4 points, 4 equal 2 multiplied by 2. So this might, very naively, you might put the conjecture that, well, maybe the number of points in the intersection of 2 algebraic curves equal the multiplication of the degree of the 2 equations. Well, let's test another case. Let's go higher. So we here have a parabola, this red parabola, and here we have like a cubic curve, and we see the intersect in 6 points, 1, 2, 3, 4, 5, 6. And 6 equals 3 multiplied by 2. 3 is the degree of this equation. 2 is the degree of this equation. So you still have this numerical equality. And I mean, if you have 5 examples, maybe for a physicist or for an engineer, that's sufficient to make a theorem. But as a mathematician, you want to study this more and to also have extreme cases. But at least we have a good question. The question is, how many points can lie in the intersection of 2 algebraic curves? Can they be infinite? Well, that's an easy question, because you can also repeat the same curve. You have a line and the same line. They have infinitely many points in the intersection because you are intersecting the curve with itself. So that's really easy. But assuming it is finite, which happens like most of the time, what is the number of the points in the intersection? And can we relate this number to the degrees of the equations? Of course, you have to count things with multiplicity, because that's the same phenomena we have in one variable. And that's a question that is geometric, and it has to do also with enumerations. You want to calculate, you count stuff. So that's some kind of enumerative geometry. But you have to be more careful. And here, because we actually need to go to projective space. For example, if you start with 2 lines, 2 parallel lines, even if you start to calculate the complex solution, there will be none, because they are parallel. So you cannot have, I mean, if this question is correct, if the answer is yes, then these 2 lines intersect in 1 point. But obviously they don't, because they are parallel. So you can say they intersect at infinity. And think about it. Think about the railway station. When you see it, you see these 2 like parallel lines. They intersect on horizon, right? You see they start merging together in the horizon, and they become 1 point. And that's what we mean when we say 2 parallel lines intersect at infinity. That's at least the intuition. And projective geometry precisely try to formalize this intuition and give a precise mathematical sense of these points at infinity, and what does it mean to intersect 2 lines at infinity. So the point here is, this is an interesting question. If we want to answer it in an interesting way, we have to go to projective space, which we will do next time, not today. Today I'm just doing things just with equations as easy as we can. So at least we have 2 things that we need to do if we are interested in solutions of equations. We have to do it over the complex numbers, because real numbers are not sufficient. And we have to go to projective space, because parallel lines don't intersect in the plane. That's the main idea. So we want to do complex projective geometry. That's to a first order approximation, what algebraic geometry is all about. Okay, so more examples. Now, instead of working with algebraic curves, meaning 1 equation in 2 variables, let's do more variables. So let's have 3 variables. So I give you this equation. I don't know whether you like it or not. It might seem to you either too easy, too simple, or too complicated. But let's study its roots. The points in R3, which are like roots of this equation. Okay, I have a question for you. Do you think that this space, this surface, has a line inside it or not? Please write in the comments. Just some guesses. Do you think it has a line inside it or not? Tell me. At least for those who don't know the answer already. Okay. Muhammad is saying yes. Any other guesses? Nice. Maybe that's too easy. Yes, okay. So how many lines do you think it has? Okay. 3. Hassan says it's 3. 3 lines, nice. At least 3, nice. No lines. Okay, nice. So, you know, people say it's 3, people say it's 0. If you know the answer, you know it is more than 3. But at least let's see how this curve looks like. So let's go out for a moment. So this is the curve, by the way. Can you see it? This is a surface, sorry. This is a surface. It is called Klipsch surface. It is very beautiful. And I don't know, at least seeing this curve, it might not look like that it has a line, but let's see this video and it actually shows how many lines do we have. So this is still the same surface. And let's now see, you see, those are the lines on it. You try to stop this and count them, you will find it has 27 lines. Not 3, not 4, not 5, 27. You might think, okay, Fauzi, you are giving us weird equations and very special cases, but actually it turns out if you do it in the correct setup, meaning complex projective curves, complex projective geometry, any such surface, which we call them smooth cubic curves, turns out to have 27 lines. Why 27? Why not 28? I mean, there are several ways to justify the 27. Some of them are very elementary, some of them are too sophisticated, but it is very interesting, something very surprising here. And that's also some other feature of algebraic geometry. You want to enumerate things. So you are given in a space. So for example, here you are given this surface and you ask how many curves this surface has, but you ask how many curves of a specific type. For example, here we are asking how many lines. You can fix some curve inside it, and you say how many lines intersect this curve, for example. So you want to try to count and enumerate geometric objects inside your space which satisfy some properties. You want to enumerate stuff, and you might say, who cares? Who cares about enumerating stuff? But people doing string theory care in some cases. And many other people care about this stuff. In physics, it has surprising applications. Okay, so now at least we have seen some examples and some questions of what is algebraic geometry all about. Another feature of understanding that I told you about is parametrizing. So let's see some kind of an example of this parametrization. So here, the main question is, can we parameterize algebraic curve using rational functions? So let's see. Also trying to interpret this question. So here we have a circle, which is given by this equation, x squared plus y squared equal to 1. And let's fix this point here, which is like at the top of the circle. And let's draw a line from this point to any other point. We will see that this line intersects the x-axis at some point t. And also, given any point t, we can draw a line from this point to the top point here of the circle. And this line will intersect the circle at some point xy. And a first question you might ask is, given the t, how we can calculate the x and y? So the point of intersection between the circle and between the line connecting this top point and the point on the x-axis. Well, that's an easy task to do. It is an exercise, in fact, and I encourage you to carry out the calculation, you will find that the x and y coordinates are given by these formulas. So 2t over t plus 2t over t squared plus 1, 2 squared minus 1 over t squared plus 1. And this is what we mean by parametrizing the algebraic curve. So here, every point on the circle except the top point can be written of this form for some t. So you just substitute your favorite t, pi, 5, your birthday, I don't care. Just substitute some t and you get a point on the circle. And the point is you get most of the point. Here you get all the point except the top point. So you can capture all the point on the circle except one point using this formula. So it gives you a very easy way, very easy to calculate some examples of solutions. So you can write this formula in a computer and generate hundreds of points, billions of points, just calculating multiplication, sums, and stuff like that. Okay, so this is an example of what we mean by parametrizing solutions. So in general, if we are given an algebraic curve by this equation, if x and y is an equation, an algebraic curve, we ask whether we can find rational functions x and y. So now x is a function of t, y is a function of t, such that when we substitute these functions, they satisfy our polynomial equation. Here, this just means if you substitute x for x, this value here, 2t over t squared plus 1, and if you substitute y for this value here, you will find that these two these solutions satisfy the equation. So if you square this thing and you square this guy, you sum them up, they sum up to 1, and the t cancels. All the t cancels, they go away miraculously. So that's what we mean by parametrizing the thing. And if this is possible, we call this algebraic curve rational. Rational because we have used rational numbers, rational functions to parameterize them. And if you don't recall what is a rational function is something like this. So it is a ratio between two polynomials, or it is a quotient of two polynomials. It is something that has a numerator and a denominator, and both of them are polynomials. Okay. So in our examples, x of t would be 2t over t squared plus 1, and similarly, y of t is given by this expression. And at this point, you might say, who cares? I don't care about rationality of algebraic curves. Well, my friend, you're wrong. You care. Why? Because you might be interested in doing calculus. You might be interested in doing integration, explicitly finding antiderivatives. So the question is, how can we in general find antiderivatives or do integration? Well, what kind of integration we can do? We can do polynomials. That's easy. We learn, all of us learn how to integrate polynomials. They are nice. We can also integrate 1 over x. And at this point, you start, as you always do in mathematics, you have a harder problem, you try to reduce it. You try to find an easier problem and reduce the harder problem to the easy problem. Here, we want to integrate something. If we can reduce it to integrating polynomials and 1 over x, we are done because we know how to integrate polynomials and we know how to integrate 1 over x. So the first things that we can reduce to integrating polynomials and integrating 1 over x are rational functions. So if we want to calculate an integral of this form, here b and q are polynomials. We learn in calculus how to do this. I'm not giving to you any new information here. This is just revision, calculus revision. And we do this by partial fractions. We take this fraction and we decompose it as a sum of simple things. R here is a polynomial, and these are just 1 over some power of x minus some c. We know how to integrate polynomials. We know how to integrate those stuff because we know how to integrate 1 over x. So this is just some simple integrals that you can do. Once you have this expression, you can do the integration using those two rules, and it is very easy. So this question we can answer. We can calculate the integrals of rational functions using integrals of polynomials and this integral. Okay, next, and this is an example of such a partial fractions decomposition. Okay, next, you might be interested in doing this integral. How can you do this integral? Well, in calculus, what you do is as follows. You say, let's do a substitution. I will call this thing under the square root y squared, and therefore y squared plus x squared equal to 1 from this substitution. And now the trick is to use the parametrization of the circle that we have done. If you substitute for x this expression, and you substitute for y this expression, and substitute everything in the integral, this is the integral you want to calculate, differentiate this and use the rules of integration, you end up with this integral. That's the integral you want to calculate now. And you notice something? This is an integral of a rational function that we know how to do. Here we have answered this question, how to do the integral of a rational function. So we can do this integral now, right? And therefore, if you can parameterize, by the parameterization of the circle, we managed to solve a hard integral. And in fact, this is not just because of this simple integral. In general, if you have an integral of this form, r is some rational function, and you have y is some square root of some square root of a quadratic equation of x, then you can do the same trick. And the key input here is that we can always rationalize an algebraic equation of this form. So this algebraic equation is rational, meaning we can find x of t, this is a typo, x of t and y of t, which solves this equation, and x of t and y of t are rational functions. And I will leave you with these two pictures. This tells you how to, this tells you how to obtain the rational expressions of x of t and y of t. It is very similar to the circle. If it is an ellipse, you fix a point and do the same trick. Take all lines between this fixed point and the point on the ellipse, and you have an intersection with the x-axis, and you write x and y in terms of the t, using solving the equations. And if you have a hyperbola of this form, you just take all parallel lines in a specific direction. For example, here we have taken this direction, and you see this gives you every such line intersects the x-axis at one point, and it intersects the hyperbola at one point. So you can also write x and y in terms of t by solving the equation of a line with the equation of a hyperbola. And this gives you the rational expressions for x and y. It is also an exercise to obtain these calculations. And actually, this is maybe just a small remark. Doing projective geometry is very nice here, because if you do projective geometry, the three calculations of a hyperbola, of an ellipse, of a circle are the same from the point of view of projective geometry, because we will have the point at infinity. But this is just meant as exposing you to the idea. The details will be covered later on. Just keep in mind that parameterizing curves is important for doing integrals. Okay, so maybe we hopefully, in a nice world, every integral can be reduced to an integration of a rational coefficient. Sorry, I don't try to move this. Hopefully, any integral can be done by substitution and reducing it to an integral of rational functions. So let's ask this question. So can we solve this integral by doing the same trick? Can we substitute y squared equal this expression here and reducing it to a rational, an integration of rational function? This is equivalent to asking whether this curve is rational. Meaning, can we find x of t and y of t rational expressions such that after substituting, we find that we have so that we are satisfying this equation? That's a question. That's just a reformulation. That's an algebraic geometric reformulation of this question. So here we are asking, can we reduce this integral to an integral of rational functions? That's a question in calculus. And you answer it by asking this algebraic geometry question, rationality of algebraic curves. So this just gives you an idea that algebraic geometry is really important. You want to do calculus, you don't care about anything in mathematics. You are a guy who want to care about doing antiderivatives all their life. You should care about algebraic geometry as well. Okay, but applications and reasons to study algebraic geometry doesn't end here. It actually starts here. So Actually, you might be interested in Diophantine equations. This means you want to study integral and rational solutions of polynomial equations. So instead of having all the complex numbers that satisfy some equation, you want to only study rational solutions or integral solutions, like integers 1 to 3. And it turns out that this has applications even in the real world, for example, in cryptography. Before we discussed this elliptic curves, something like this. And as I said, this has a group structure, and this group structure is employed in cryptography. So this is such a, and I mean the group structure here comes from the rational points, so rational solutions. And you can ask how many integral solutions exist for this? Not all solutions, just integral one. Are they infinite? Are they finite? That's a question algebraic geometers try to answer, and it is answered, but the answer is not trivial. I cannot give it in 1 hour. It would need weeks to fully answer it with all the details. Okay, so this is some other reasons why you should care about algebraic geometry, that it might have a real world applications. And as I said just yesterday, I was in a talk and they used algebraic geometry to solve differential equations coming from dynamics. Amazing stuff. So other reasons is that algebraic geometry is connected to many other mathematical branches. For example, BDEs. One connection I already mentioned yesterday in this talk, but you can also have more serious connections with via what is called Hodge theory. You have connections to complex analysis via compact Riemann surfaces. For example, if you try to pursue this connection, these elliptic curves correspond to torus. So the torus that you have, the donuts, this equation corresponds to it. So this equation topologically in complex analysis will be viewed as a torus. Crazy. Okay. Next. Topology and differential geometry. Why? Because you have differential geometry, you have algebraic geometry, and you have an intersection. And the intersection is the best of the best worlds. Because the thing is, what is the difference here between differential geometry and algebraic geometry? Differential geometry only studies smooth stuff. You are not allowed to have this node. You know, these curves that we have having this feature, you don't study this in differential geometry, but you study it in algebraic geometry. But in differential geometry, they study more stuff. They study spaces which comes from exponential functions. In algebraic geometry, you are not allowed to talk about exponential functions because you only care about polynomials. So there is an intersection between differential geometry and algebraic geometry. And and this is very interesting because algebraic geometry is very computational. You can write a program, a computer program to calculate you the homology groups, and you to solve the equations. You can ask how many functions or sections of a line bundle or whatever that exist, and you can ask computers to do this. You cannot do this with differential geometry. You cannot program it very easily because you are working with transcendental functions, which is much harder to encode on computer. Polynomials you can do because they are finite information, and differential geometers are employing these algebraic techniques to answer questions in differential geometry. You can also relate algebraic geometry to combinatorics, because in combinatorics you try to enumerate stuff, you try to count stuff, and as we have seen, some questions in algebraic geometry are about enumeration and about counting. And there is a full branch of algebraic geometry called enumerative algebraic geometry, which studies some combinatorial questions. You can also relate it to number theory, as we have seen already here. And the list goes on and on and on. But if something is already connected to so many mathematical disciplines, it might be of interest. Okay, so I think hopefully this gives you enough reasons to study algebraic geometry. Here are some questions. Base of the curve. I'm not sure what do you mean, Hassan, by the base of the curve. Okay. Okay, so we don't have a lot of time. I think we started 10 minutes late, right? So I still have 15 to 20 minutes, right, Cha?
Yeah, you can continue. I think don't go
fast.
And
yeah. So I think I will end the lecture by some formal definitions. So now we have seen that we are interested to study algebraic curves, solutions of one polynomial. Well, why not more? So why not more equations and more variables? And that's systems of equations. So here we start with complex numbers. Now we will stick to the complex numbers, and we take the polynomial ring over complex numbers. So these are the set of all polynomials with complex coefficients. And we take a subset of this. So some bunch of polynomials, complex coefficient polynomials, and we allow this set to be infinite. So you can have infinitely many equations, but polynomials. And we study the set of solutions of this infinitely many equations, for example. So this is a set of all points in Cn, such that after substitution in every equation or in every polynomial in E, you get 0. So it is a set of all points in Cn such that g of p equals 0 for every g in E. So E is a set of polynomials, the set of our equations that you want to study their solutions. And this set V of E, we call it the vanishing set of E. Vanishing set of E is the solutions of those equations. And such a vanishing set is called an algebraic set or the zero locus of E. That's the main object study of algebraic geometry, solutions of a system of polynomials. A very easy property to see is if we have a subset of a set, so if we have E is a subset of F, then the vanishing set of F is a subset of a vanishing set of E. So here we are reversing the inclusion. So the more equations you have, the more restrictions, and therefore the less solutions you have. So if you put more equations, you get less solutions, because every more equation is a new constraint, or at least it doesn't eliminate constraints. It put more constraints, and therefore you can only lose solutions. You cannot gain any solution, and that's encoded here. And the proof is just by definition, more or less. If you have a point in the vanishing set of F, it means that for every equation in F, it vanishes at this point. But this means every equation in E also vanishing at this point, and therefore this point is in the vanishing set of E. So the definition, the proof is trivial, but it is an important fact nonetheless. Okay, so the first question as a mathematician you should ask is, are we studying something which doesn't exist? Is this set empty or not? So we want to know when this set is empty. And we want to know whether we can get rid of this infinite possibility, because here we just said take infinitely many equations, that's fine. But the question is, can I only use finitely many? So if you give me an infinite number of equations, can I find only finite number of them that whose vanishing set is the same set? So I start with V of E. E is an infinite number of equations. Can I find a subset of it? Subset F, which consists only of finitely many equations, such that the vanishing set of F is the same as the vanishing set of E. So here we are moving from an infinite number of equations to a finite number of equations. Is this always possible? Why do you care about this? Well, you care about it because, again, of computations. If you want to implement this on a computer, you cannot give a computer an infinite number of equations. You can, the most you can dream of to give the computer is a finite number of equations. So if you want to make your theory computationally possible or feasible, you have to answer this question in the positive. And this question, the first question about the non-triviality or the non-emptiness, is to ensure that you are not talking about the empty set. There is no geometry of the empty set, at least that I'm aware of. Okay, so let's try to answer the first question partially. Well, there is what we call a trivial abstraction, meaning that it might be empty for trivial reasons. What trivial reasons we have? Well, suppose you are given some polynomials, some equations, f1 up to fn, and these are inside our E, the set of equations that we are interested to understand their solutions. And suppose we can find some more equations, g1 up to gn. Here, I mean, this number of equations doesn't need to be the number of variables. So this is better fl or fk. And suppose that we have an identity like this. So given f1 up to fn, suppose we can find g such that this solution, this identity hold. Then there cannot be any solution. F of E must be empty. Why? Because if you have an element in a point in F of E, we will get a contradiction. Simply, we have 1 equals 1 of B, because 1 here is, this one is like the constant polynomial. So it is not the number 1, it is a constant polynomial 1. So 1, the number, equals the constant polynomial at B. And by substituting this equality here, because B is in in V of E, and E contains this polynomials f1 up to fn, we will get that f1 of B is 0, f of B is 0, and therefore everything here will be 0. So you will get 1 equal to 0, which is not true. So this means that we cannot have any point inside the vanishing set of E. So if this condition happens, we are ensured that there is no solutions in V of E. The question is, that's a trivial obstruction, a trivial reason for why no solutions might not exist. The question is, can we have non-trivial solutions? Meaning, can we find cases where there are no solutions, but this phenomena doesn't happen? So there is no G's making this equality whole, but yet there is no solution. That's the hard part, right? So here we have just only covered the trivial case, and later on we will tackle the less trivial case. But at least, is the question clear? Please write me in the comments. Do you think it is clear or not? Because if it is not, I need to explain it better. Anyone? Is it okay? Okay, nice. Yes, nice. Okay, so the first question was about this one. So here, when I say there exist polynomials G1 up to Gn such that this equality holds, this one here is not the number 1. It is a constant polynomial 1. So a polynomial can be, so you say f of x equal 1. That's a constant function. It is a constant polynomial. So 1 here is not a number. It is a function. It is a polynomial. So that's the 1 here. So this equality means that 1, the number 1, equals the value of the constant function 1 at the point B. That's by definition of the constant function. A constant function is a function whose value at every point is constant, meaning 1 value. So that's the first question. Okay, and why the f's are 0? Simply because I am here assuming that the f's are in E, and I am assuming that P is an element of the vanishing set of E. The vanishing set of E means the set of all points B's that after substituting in F, they are 0. So this precisely means that F1 of B equal to 0 and Fn of B equal to 0. So this is this part. And now this equal to 0. So we have 1 equal to 0, which is a contradiction. That's the first thing. That's what we call a trivial obstruction. The question now is this the only case in which we don't have solutions? Meaning, can we have a situation where our polynomials are such that we cannot find any G's making this equality hold? So we cannot write 1 as a combination of the F, but yet there is no solution. Here we have seen that if we can write the 1 or the constant function 1 as a combination of our equations, there is no solution. The question is whether the converse is true. If we have no solutions, then we can write 1 as a combination of the equations. So on one hand, we have writing 1 as a combination of equations. On the other hand, we have emptiness of solutions. We have 1 implication. The question is whether the reverse happens, the converse happens or not. That's the question. Is it clear now? At least people who ask it to repeat it. Is it clear? Yes. Nice. Okay. So, okay. At least now you see that studying the combinations of the equations is important. Because here, for example, in this case, we have used this idea, writing combinations of equations to ensure that there is no solutions. And actually, as a remark, if you have some polynomials and you have a point which is a 0 of those polynomials, any combination of these polynomials is also 0 when evaluated at this point. So if you have functions or polynomials f1 up to fk, and you take such a combination here, any g, like you can choose whatever g's you want, and you take a point p, which is a 0 of fi's, then if you evaluate this combination on this point, it is still 0, because again, it is the same proof. These fi's are 0, so the whole sum is 0. So if we are given an algebraic set like this, we can enlarge the equations by taking all combinations of the equations. So we start by, let's say, 5 equations. Take all combinations. This infinite set of equations now it's actually an infinite set of equations, because you are taking all possible combinations, multiply the first equation by x squared and some x cubed to the second equation, blah blah blah, do whatever you want. You will not lose solutions. The new system of equations, which is now infinite, have the same solutions as the initial equations that you started with. So this means that even if you start with a finite number of equations, you can generate infinitely many equations which have the same set of solutions. You might ask, why should we do this? Why to go from a finite number of solutions to the infinite number, from a finite number of equations to an infinite number of equations? Well, to our surprise, this makes things easier, and we will see why. But let me see the question again. If b is the zeros of f, then the product of f to any function. Yes, Hussein, yes. This is the correct also explanation. Yes, thank you. Thank you very much. That's a correct explanation as well. And when you sum zeros, it is still zeros. Okay, so, and this gives us the idea of an ideal. So if we start by a set of polynomials, we define the notion of an ideal generated by this. Those who have taken some abstract algebra know this notion already, but we should recall it. So it is the set of all combinations of elements of E. More precisely, we take all combinations of this form, where the g's are polynomials, and this k is just some positive number. So 1, 2, 3, it is not fixed. It can be 1 million, whatever. And we took all those combinations, put them in one set. We call it the ideal generated by E. Okay, so we are taking the set of all combinations of this form, and we call it the ideal generated by E. And remember, E might be finite. It might be one equation. So in this case, if E is one equation, we are taking one equation and multiply it with all polynomials, and that's now our ideal. Okay. And by this remark here, you can see that the vanishing set of E is a subset of the vanishing set of the ideal generated by E. So remember, you said if you have more equations, this has like more restrictions on your solutions. But in our case, when we move from E to the ideal generated by E, we have no more restrictions. This is a very special case. We don't have more restrictions on us. So this is not true in general, but it is true for ideal generated by our set. Okay, and why should we care? Because of this proposition. So simply as a slogan, you might remember it as combinations are our friends. So meaning that if you take the vanishing set of a set of equations, a set of polynomials, it is the same as taking the vanishing set of the ideal generated by this set. So V of E is the same as V of the ideal generated by E. Already we have seen one inclusion here, and the other inclusion comes from inclusion reversal. So remember, we said when we have a nested subset, we have E is inside F. F here is the ideal generated by E. We taking the vanishing set reverses the inclusion. So this will say the vanishing set of the ideal generated by E is a subset of the vanishing set of the vanishing set of E. So this gives us one inclusion, and here we have already seen the other inclusion. This tells us the vanishing set of E is the same as the vanishing set of the ideal generated by E. So you don't care about the proof, okay, that's fine. Just remember that combination is your friend, meaning that if we start by some equation, we are interested in their solutions, in their roots. We might take all combinations of these equations. We are not changing the roots. So we are changing the system of equations, but we are not solving, we are not changing the solutions themselves. And you might think of it something like what you do in linear algebra. You are given a system of equations, you want to study them, and you want to solve it, and you solve it by changing the system itself. You say, I will multiply the first equation by 5, I will multiply the second equation by 6, I will add those two new equations to cancel something. That's what we are actually doing here. We are just multiplying the first equation by something, the second equation by something, summing them so that some cancellation happen, and we are giving new equations. But the trick is this system of new equations have the same solutions as the old system. Yes, we might have new equations, larger number of equations, but the same solution still are there. So it is very similar to what we are doing in linear algebra. Now we are just multiplying equation not by numbers, but by polynomials. That's the new thing. Okay, so you might check that these ideals are satisfy some properties. So, for example, 0 is always in the ideal. The difference of two elements in the ideal is still in the ideal. And if you multiply something from the ideal with any polynomials, the product is also in the ideal. And you should check those properties. It is a very important exercise. And actually, in abstract algebra, this is taken as a definition of an ideal. So in general, if you have a ring, an ideal is just a subset, I, which satisfies these three properties. So these are like the abstract properties of an ideal. Here we have defined the ideal explicitly by as a set of elements, and we should check those properties. Okay. So ideal in general meaning a subset which satisfies these properties. And there are two main examples of ideals. Well, the polynomial ring itself is an ideal, and it is generated by 1, the constant polynomial. And we call it the improper ideal, and any other ideal is called proper. So proper means it is not the whole thing. It is proper. It is small. It is not the full thing. And the other important one is the trivial ideal, and this is just the set of 0. Like the 0 polynomial is an ideal. You can check it satisfies this. Of course, 0 is in here. If you 0 plus 0 is 0, you multiply anything by 0, it is 0. So 0 satisfy all these three properties. So the set of 0 is just an ideal. And also the polynomial ring satisfy these three properties. So these are two main examples of ideals. And now let's try to answer our two questions. If you remember here, those two questions, whether it is non-finite and whether it is non-empty and whether it's finite. We talked about ideals to be able to solve these two questions. And let's, before we do it in the general case, and I know my time is almost done, but I'm also almost done. So let's do it in the case where n equal to 1. So n was the number of variables. So here, this means that we are having one polynomial or working with polynomial in one variable. So the first equation says, can we find, if we start with an infinite number of equations in one variable, can we find a finite subset of equations whose solutions are the same as the solutions of the initial system? So the initial system is E. This might be infinite. We want a finite subset of equations which have the same solutions, and we are working in polynomial ring in one variable. The answer is yes, and this is because we can use now ideals. So V of E equals the V of the ideal generated by E. That's we know. And you have an ideal in this ring. An algebraic fact tells you that you can always find a polynomial f such that this ideal generated by E is also generated by f. This fact is known as a slogan. You can say that C of X is a principal ideal domain, for those who know this term. And this is just a factor from algebra. And how it is proved, it is just the fact that you can divide polynomials. You have a division algorithm. You can divide polynomials in the same way you can divide integers. And if you write this algorithm in the correct way, it just tells you, given a bunch of polynomials, you can find one polynomial which such that all those generators are just multiples of this polynomial. And how do you get this polynomial? Actually, you take this ideal generated by E, and you take any polynomial of minimal degree. So this ideal is a bunch of polynomials. Take any polynomial of the smallest possible degree. And if you do this, you can prove by the division algorithm
that the ideal generated by E is also generated by F. Therefore, this question here is easy, and it is easy because every ideal in CX is principal, meaning you can find one element in it generating it. But the upshot here is to answer this question, we had to go through ideals. We started with a bunch of polynomials, and to employ these results, we have to talk about ideals. That's the point. That's where the algebra come in. We are interested in solutions of polynomials, and to answer this very first easy question, we had to go to ideals. Second question is whether there are non-trivial abstractions. And this also can be answered here very easily by the fundamental theorem of algebra. Because if we start again by any set of equations, we can choose this magical equation F, whose solution is the same of solutions as E. And we know by the fundamental theorem of algebra that if this F is not constant, then we have a solution, a complex solution, of course. So already in one-dimensional case, or in one variable, we have answers. And the natural thing to say is, what happens if we are now working with several variables? Instead of one variable, we have 15 variables. Then we need a generalization of the fundamental theorem of algebra. And we have a generalization of the fact that ideals are principal in the polynomial ring. I think I don't have any time, so I will not proceed further. But in fact, just to give you a teaser of next time, we have two theorems. One of them is called the Nullstellensatz. Nullstellensatz is a German word for saying zeros of the proposition about zeros. So, and even in like English literature, it's called Nullstellensatz. It is not just in Germany. In any algebraic geometry book, they keep the German word for some reason. And we will discuss it next time. But what you should remember is Nullstellensatz is just a generalization of the fundamental theorem of algebra. And another theorem which answers the second question is what is called the Hilbert-Base theorem. So next time we will start with these two theorems. We will go through them. I will not give you a proof, but I will tell you where you can find a very easy proof, because this theorem, the Nullstellensatz, somehow many people don't prove it. They view it as a hard theorem. I know why Shah is laughing. We have common stories about this, but anyhow, I will actually tell you where you can find a proof. Maybe I will also present it, because next time I think I will have more time, so I will present it. And the proof is really, really elementary, that a student in first year mathematics can understand it. If you know what is an uncountable set, you can understand this, because it just uses the uncountability of real numbers. That's it. So next time also we will talk about the Zariski topology, and we will talk about irreducibility. We will start relating algebra and geometry. Already here you have seen that study of solutions has to do with ideals. Ideals are algebraic objects, and the next time we will study the algebra geometry dictionary. To motivate things, I will do it first in the differential geometric setup, talk about why algebra is important in differential geometry, and motivated by this, we will do it in algebraic geometry and see how algebraic sets actually correspond to specific type of ideals and also to specific type of rings. And at the end, we will discuss projective space. This is, I think, also very important, because to do algebraic geometry, the correct language of algebraic geometry is, in some sense, the projective language. Also, depending on time, we will talk about art, because projective space and the projective geometry actually came up from art, because projective space, projective here comes from the word perspective, how you see things through your eyes. You know, as humans, we see things through our eyes. So, and the geometry from our eyes is different from Euclidean geometry. Again, you have two parallel lines. You have these two lines of the railway. You see they intersect at the horizon. That's what we see with our eyes, even though geometrically in Euclidean geometry they are parallel. So projective geometry gives a meaning, or projective space gives the meaning of this intersection at the horizon, or intersection at infinity, and it is because we see the world through an eye, you know. And the projective geometry is just doing geometry from the human perspective, doing geometry from perspective. And this is the correct language of geometry somehow. And if there is any catch in this is that, you know, human eye is important because it gives you a very interesting geometry. And yeah, so maybe I will also talk about history a little bit because I think it is a fascinating. So this is the plan, the agenda for next time. And some of those topics are more abstract than others. You don't need to know anything about topology. I will, because we are working with a specific example of a topology, so we will just introduce it, we will use it. And already now I can give you the definition, but we don't have time. Yeah, that's the plan. If you have any questions about today or next time, please write me in the comments. Yes, so Muhammad asked if C of X is not a principal ideal domain. Will it be true? So yes, it is not true because in general, the polynomial ring in several variables is not a principal ideal domain. I'm not claiming it is a principal ideal domain. That's why I said we need a generalization. So it turns out, even though it is not a principal ideal domain, it is what is called an Noetherian ring, meaning that all ideals are finitely generated. So just to burn the next time, you start with an infinite number of equations, take the ideal generated by them, and using Hilbert basis theorem, you see that this ideal is finitely generated, and therefore you can find finitely many equations. That's answers this question. More importantly, and this maybe will be answered only at the end of the final talk, you might ask, can we actually calculate those generators? The answer is yes. There are algorithms. You can ask the computer to give you those finite generators. But that's an algorithmic question that we might touch on. Yes, Muhammad says if f is a field, then f of x is a principal ideal domain. Yes, but a polynomial ring in several variables over a field is not necessarily a principal ideal domain. Actually, once you have two variables, it is never a principal ideal domain. Well, guys, you seem to know a lot of algebra already. I might next time talk about the schemes then.
I think there's a very small size of the...
No, I'm just joking. I'm just joking.
Thank you very much for this. It was very interesting
You're
piece
welcome.
of math I've ever seen. So anybody, if you have questions, you can unmute yourself and ask, or you can write down and comment.
Yeah, I forgot to say thank you for attendance, and for those speaking Urdu, I think it should be shukriya, and for those speaking Arabic, shukran.
Shukran.
I might want to say manana.
Yeah, manana. Thank you.
Okay, I think I should stop recording now.
I think
then
there was
we
also a
can-
question about books. Yes.